So let's take a look at this one here, stack protection, where you get to see how well ASLR works. And as I've said, not as much as it should. So we can observe it. This program, ESP3, I've already put it in here. If I do a directory, I can type esp3.cpp. All right, I can probably make that, oh, I can do this actually. Yeah, cool. Microsoft finally learned how to give us Control Plus. So anyway, so this is how you have inline assembly in C. So I added inline assembly, it takes the ESP and moves it into the thing called data, and then I can print out the data. So that's all this does. So if you run that, oops, I don't need the dot slash. Right, it just tells you an address for where the stack was at this point in the program. And the interesting thing is, it's changing, of course, as it should, because this has address space layout randomization. So you see the last byte is always C, but the rest changes randomly. All right, so that shows it. Now we can compile it normally and show that it's random. And we can also compile it without ASLR. And the way you do that is with CL/C and then link dynamic base no. Those are the steps that make a program without address space layout randomization. So that's ESP4. Oops, not listening to me. All right, and if I run this one, it's the same every time. So the program is compiled without the ability to randomize in memory. So we can check the randomness. And you can just write a Python script. We have Python 2 because it comes with immunity. So you just write a script that's going to run the program a certain number of times. And when I run the program 10,000 times, it takes a few minutes to run, but I did that here, and you get 10K, about 85,000 bytes of characters. So if you, that's just going to give me a lot of these addresses like that. And the interesting thing is, how different are they? And to find out, you can just find out with another Python script. Now, the first thing I did was find out where things are on my machine. On my machine, without any address space layer randomization, things start with 19FE. So I modified the count program. Now, when I prepared this before, it was 19FF. So on my machine, it's 19FE. This is going to check to see if it starts with 19FE. This is a regular expression. So this is going to go through all the lines, all 10,000 lines, and show me the ones that match that pattern. So if you run that, Python count. There, doesn't take long, and it finds several. So if I do 10,000, 3 of them were not randomized. Although there is a third byte here, so maybe I should, but anyway, 3 of them were pretty close to what I expected. So that means I have a pretty high chance of succeeding with maybe 10,000 guesses, which surprised me. And it turned out to still be the same on Windows 11. So that's rude. Anyway, that's how it works. And if you download my file and analyze it, you'll find the flag, of course. Yours is going to be random. Anyway, so now we can view memory sections. So this ESP4, if you run this in Immunity, guess I will, ESP4, that's the one that's not randomized. Let me run this in Immunity. All right. And so let me make it bigger, there, if I can get it to listen to me. There we go. Whoops, still not listening to me. There we go. All right. So if I open ESP4, okay, and now I view the memory. Because it's not randomized, it loads right where it wants to load at 400,000. The header is at 400,000, the text is at 401,000, and so on. This is where things load when they are not randomized. They really load at 400,000. All right, so now I can run it, and this program just prints out a bunch of addresses of objects on the text, data, heap, and stack, and then it prints out the first 10 values on the stack. So if I compile it normally, with all protections, I get mem.cpp, and this ends in a breakpoint. So I had to recompile it to get rid of that. And anyway, I'm just going to get to the interesting point here. After you remove the int, which was there so you could do it in the debugger, you can then examine how random things are here. I was doing that before, so that's dir shows me I have mem.exe, and then CLS. That'll just put it Okay, I'm doing it wrong. I'm going to do CLS and mem. Now this is just a way to make it dynamic. There, now it'll always be at the top of the window. And so if I run it again and just see what's changing, you can see the first two addresses don't change, but the second two do change. And if you look at the stack, you can see the second number on the stack is 32, now it's 30, now it's 30, so the second number is changing, and the fifth number is changing. And if you read, we talk about what those are. Word 1 points to an address on the stack. Word 5 is the stack cookie, so it's random every time. Word 6 is the saved EBP, so it has to move along with the stack. And word 7 is the return pointer, which points to something in the text section. And what's interesting is word 7 is the one ending 337 is the return pointer, and it never changes. So if you were able to jump to the text section, it doesn't randomize, which strikes me as a weakness, but that's the way it is. Anyway, that's the thing. Now you can also compile the program with no protections. That's what this is going to do with these switches. It's going to turn off all those defenses. And give me the same source code and just recompile it and link it differently. Now mem0.exe should have none of those defenses. And now I just want to run this one dynamically. So clear the screen and run mem0. Okay. And now the stack doesn't move. The fourth number shows the stack. Now the address in the heap changes, but I don't think it's because the heap is random. I think it's because when I allocate space in the heap, it doesn't just give me the first space. I think I guess it's randomized, but it's not randomized from ASLR. I think it's just the way the heap is used. And so you see now on the stack, all these numbers stay the same. The only one that changes is 6 and 7. 6 and 7 both change, but all the rest stay still. 6, 7, and 8 change. And let's see, yep, so all these, 6, 7, and 8 are in the calling function stack frame. So that's why they're not in this function. So none of them move. So that's what you do is turn off these defenses. Everything becomes predictable. And that's what I wanted to show you for this one. So let me stop this one.